So I'll be talking about observations of the internal motions of galaxies from redshift 3 until now. And so there's going to be no simulations until the very end of this talk. It's all good. Thank you, Richard. It's all good. So some of the work I'll be presenting is from the PhD thesis of my student Raymond Simons, who's talking tomorrow afternoon. He's applying for jobs in the fall, and I cannot recommend him highly enough. As you can see, he's dual observations and simulations. So disk galaxies locally are well ordered, and the gas and stars go around beautifully along the center, and the disk is quite thin. This is not a simulation. This is a Hubble image. I peppered it with Hubble images because I'm from the Institute, and they're beautiful. So the questions I want you to be thinking in the audience is when and how are disks assembled, and when and how do disks settle into their current well-ordered state? And that's a hint at the results and that they're not always in this beautifully well-ordered state. So this is a nice plot from Peter Van Dokkum's 2003 paper. And it's representative of a number of pieces of work that have showed that at redshift 2, Milky Way progenitors are already in place. They don't look like the Milky Way back then, but they are smaller. So these are Hubble images, and the last one's at redshift 0. It's like Sloan images. And if you've been reading the literature, a lot of there's some very large IFU kinematic surveys of galaxies, and a lot of what they're saying is that disk galaxies are already in place at a redshift of 2. There's a Nature paper on a number of Nature papers on these beautiful disks, awesome data. There's a recent review that says a key point has emerged from this activity is that substantial fractions of higher redshift galaxies have regular kinematic morphologies despite irregular photometric morphologies, saying they might look weird, but they're disks kinematically. And then this beautiful data from the Kamo Survey you'll be hearing all about on Friday. One of their main conclusions is that 83% of resolved galaxies, these are all star-forming systems, are rotation dominated, determined from a continuous velocity gradient, and V rho over sigma greater than 1. We'll talk more about this later, implying that the star-forming main sequence is primarily composed of rotating galaxies at redshift 2 and at redshift 1. So we're addressing this with data from the Deep 2 and from the Sigma surveys. They're at redshift from 0 to 1 and around from 1-ish to 2.5, using Keck Demos and Keck Mossfire at redshifts 1 and 2 respectively. One thing that's important about this survey, I should say, is that there's no cuts on galaxy morphology. We look at all star-forming systems. And we measure, we get emission lines from spectra, and from those spectra we measure kinematics. And I know I'm showing a spectrum to a simulation audience, but I just want to get across the main point here is that it's very important to take into account the effects of seeing and essentially beam smearing when measuring kinematics. And what we found is that at high redshifts, many galaxies have a high velocity dispersion, and that's not solely accounted for by seeing. So we measure rotation velocity and velocity dispersion for galaxies from redshifts 0.2 essentially all the way out to 2.5. And these are 3 example galaxies all at a redshift of 1. And you can see this is a rotation dominated system. It looks like a disk galaxy, like local more or less. This is a sigma dominated system, and this is something that's a bit in the middle. So we measure V rho and sigma. V rho is essentially V flat of the rotation curve you're all familiar with local galaxies, but sigma is not. Sigma is measured from the gas, and it's measured in this giant slit across the galaxy. And because of that, it doesn't measure pressure support. It's not measuring a thicker disk. What it is, because unlike stars, gas is not collisionless, and if you throw it to the center, it shocks and it does odd things. So what it measures is all the velocity gradients in the gas beneath the seeing limit. So it's a gas velocity dispersion, integrates overall velocity gradients beneath the seeing, and in these papers we argue it quantifies the amount of disordered motions in galaxies. So you can see all the odd things going on here. They're all beneath the seeing limit pretty much. We sum them up and they go into sigma. So I encourage you to see all these papers listed here, especially Covington et al., where we investigated that in more detail using simulations. Okay, so now we have these 2 numbers we measured from the emission lines in galaxies. They quantify the kinematic state of the systems, their V rho and sigma. How do these evolve with time? So for 2 samples of galaxies, we have a high mass sample, 10 to the 10 to 10 to the 11, and 10 to the 10, 9 to 10 to the 10. We look at how the velocity changes with redshift and how the velocity dispersion changes with redshift. So very interesting with the velocity, this is at a fixed mass. So at this mass, at each redshift, the velocity for the high mass galaxies is about constant. For the low mass galaxies goes up with time. Time goes from here to here, as you know. Velocity dispersion very nicely goes down precipitously all the way up to redshift. This trend continues all the way from redshift 2.5 to now. And there's a fit to that. So what happens when you essentially link galaxy populations in time with something like abundance matching? You find similar trends. You find that the velocity goes up. Here we have 3 mass bins for fun. Here you have the velocity goes up with time for all the masses, and then the velocity dispersion drops. And as you know from the local universe, the more massive the system, the faster it rotates, and the less massive the system, the slower it rotates. Sorry, the numbers should be swapped there, but velocity V over sigma is correlated very nicely with the morphology of a galaxy. And I put this slide in here to remind you that sigma is not just a thick disk, as you might think. What it is picking up some of these odd motions. So again, these are redshift 1 galaxies in order of high V rho over sigma to low V rho over sigma. And by eye, you can say, all right, a V rho over sigma of about 3, we're going to play with this number in a bit. Kind of by eye separates the more disky systems from the more visually disturbed systems. So we're going to play this game. How does the fraction of disk galaxies evolve? We're going to define a disk galaxy by V rho over sigma. Locally, a galaxy with V rho over sigma about 10 is common. That's what we find local universe. All these galaxies I'm showing you here with the Hubble images, V rho over sigma greater than 10 for sure. Now we're going to look at how V rho over sigma greater than 3 evolves, because it's very rare in the higher redshift universe you're going to find something so settled, so well ordered. And we're going to look at a very simple criteria that people use a lot in the literature, V rho over sigma greater than 1, or simply a rotation velocity that's greater than its velocity dispersion. So here is the fraction of galaxies already from now, just about to around redshift of 3, with the fraction of galaxies with V rho over sigma greater than 1. And what you see is that with time, the fraction increases. I like looking at things with time because I'm an observer, I guess. At any point in time, the higher mass systems always have the largest fraction of disk galaxies, or the largest fraction of galaxies with V rho over sigma greater than 1. And then to just remind you, there's these beautiful IFU surveys at redshift 2, 1, and even less than 1. They get full kinematic maps of the systems. And then they publish awesome papers. And I just want to show you that we are all quantitatively in agreement. You see, once we take into account the stellar mass of the surveys. So here is the Kamo 3D survey. They're right up here, and they're consistent with our higher mass systems. Here's the KDS survey, the images survey, cross, massive, so on and so forth. We're all pretty much in agreement once you take into account stellar mass. So now let's look at the fraction of V rho over sigma galaxies with V rho over sigma greater than 3, and you can see even that's quite lenient to call a disk something with V rho over sigma greater than 3, and you can see you get the same trend in that this fraction just precipitously decreases as you look back in time. And if you look at even the higher mass systems here, this is in red, only 30% have V rho over sigma greater than 3. So I argue that really most galaxies at this point in time are just assembling their disks. They're just first acquiring angular momentum. And as you go to lower masses, further periods in time, you have a disk there, but it's still settling with time. And it's very beautiful to see these beautiful average trends in the data. Although at any point in time, there's a lot of scatter. So you're going to see some disk-like galaxies at high redshift, as we've seen in those beautiful nature papers, but they're rare. They're very rare systems. So what do you think is going on? First order, I say, well, this likely reflects a decline in star formation rate. There's less feedback, less minor major mergers going on. Galaxies are left alone, and they can do their thing and spin up and decrease in sigma. They just kind of, I think, slowly acquire some material. Higher mass galaxies arrive at the kinematically ordered state first. We call that kinematic downsizing. And then conclusions from high redshift surveys depend on sample selection for mass and morphology. I want to drive that point home. We're not in disagreement at all. And these are powerful constraints for your simulations. I challenge you to try to match this and try to figure out what exactly it's due to. These are very hand-wavy suggestions. Here's some more hand-wavy suggestions that I think if you look in detail on your models, it might be due to, and I'll just show you some examples just right now of some mock observations of simulations that we get a hint that some of these processes are in play. One of them is feedback. So, you know, as your star formation trails down from redshift 2 to today, there should be less and less feedback going on. Is feedback causing the sigma and then just the decrease in it causing sigma to go down? Is there just simply less minor mergers, less stuff falling into the galaxy over time to rile it up? Is that what's causing this beautiful decrease in sigma? What about the lack of gravitational instabilities over time? A decreasing amount of clumps, is that related? Or is all this related together? Is all this part of the story that your simulations are trying to tell us? It's unclear to me which processes are at play and when. I really don't have a constraint on how to, I really don't have a way of constraining this from the observations alone. I need your help. So do simulated galaxies undergo disk settling? Let's take a poll. How many people think that your simulation personally will do this? Awesome. Well, at least the front part of the room thinks so. The answer is correct. They seem to do this. And when I have people do it on the slide for me at conferences, they're like, wow, it matches really well. We don't, and I ask them why, and they're like, I don't know. So this is a paper I did with Alison Brooks and Fabio Governato back in 2014. We looked at just four of their galaxies, and this is the average the average from them is these red and blue lines for cold and warm gas. And we took what we could from the simulation output, and essentially this is the observation gas, which is kind of right in between. And it found the same slope, and it hit right in between like we expected. It was a little weird. And the same thing for rotation velocity. Their systems were higher mass than us, but we found this similar slope, and I was kind of weirded out by that. So maybe there's something fundamental in these simulations that you guys are just getting right. Maybe. And so also Daniel Severino looked at one of his Vela simulations, and many of you in the room were involved in this. He looked at a low mass galaxy, an Agaros simulation. Oops. It says Vela here. Oh, I put Vela there. It's an Agaros simulation, correction. And then he flips it and he looks at sigma over V rot versus redshift. This is my 2012 paper up to redshift 1. And he runs it twice. And I like this very much. You run it with and without stuff, and you see what happens. He runs it with the feedback. I'm sorry, he first runs it without the feedback, right? And he finds this. So this is without feedback. That's the evolution of this one galaxy. And then with the feedback, it's almost right on the data. And this is interesting. So in simulations, sigma seems to be caused by things like, less and less feedback over time, less and less clumps over time, galaxy interactions, gravitational stability, minor mergers, so on and so forth, in a broad brushstroke sense. But I think we really need to hunker down and figure out what exactly is going on. I think this stuff is a very nice constraint for your simulations. I feel like the parameter space of the physical processes in the models are not fully explored. It's important to turn things on and off and turn the knob up and down. And if you don't get a galaxy disk, I think that's very interesting and worth publishing. And observers would like to know about that. We use V-rot and sigma evolution with redshift and mass as a constraint on the physical processes such as feedback. So if you're tuning your feedback, maybe getting these relations down would be a good constraint for you, especially at lower mass. We find some interesting things locally at lower mass too, in the kinematics. So we also learn things when hydro simulations don't match the observations. So please publish when you don't. I like to read your papers and get a hint as to what could and couldn't be going on. Keep going. Then cut back publishing your beautiful disks. Okay, so I just like to end with this plot. This is the abundance match population plot, where again we find that rotation velocity of galaxies goes up with time, and that at any point in time the higher mass galaxies have rotating faster, and then the velocity dispersion goes down with time and is absolutely independent of galaxy stellar mass. And I want to ask you, can your simulations produce this? Yes or no, and why? Yes, thank you.
Another talk ending early. This is surreal. Questions?
So Linda Takani is doing it, and she'll speak about this on Friday. For the ones that she published, they agree quite well, but I know she's done a lot more that is still being analyzed.
But